You might be thinking that these are some pretty cool or pretty decent NeRF looking images. And you would be right, this is a NeRF, but it's actually a single image that generated these, which is what this paper proposes. So basically, you give it an image and it produces a 3D representation of that image. And this is the first model I've seen that actually does like a pretty good job with it. 'Cause, I mean, these images, these are pretty good. It's literally a single image and it generates all of this. Some of them have pretty good detail in there. Yeah, there's some more down here. You can play around with this giraffe, and it looks a bit weird, but like the main shape is there. This one has a little more texture to it. And there are some more down here that my tablet cannot load, but yeah. This is the paper, LRM, Large Reconstruction Model for Single Image to 3D. So one image, produce a 3D representation of that image. To start, just hop into it. So this is the model here. And basically, what they do is they collect this large data set of 3D objects. Well, they don't collect it, but there exists a lot of 3D object data sets. They list them all down here. Down here. And they list them all, but there's a lot of right here. So Objaverse, MV ImageNet, some more. So you basically have this data set of 3D objects. And what you can do is you can basically pose a camera around those objects, like a virtual camera, to get a 2D representation of that image. And basically you want to train your model so that it's given this 2D image here, and then it produces the 3D image that went with that object. So yeah, this is the model, and we'll just go through it step by step. It's a pretty cool idea how they do this. So yeah, let's just get into it. So the first thing is, how do you encode this image? So if we look right here at the top, we'll just start here. Yeah. So if we look here at the top, you can see that they have this part here. So this part here is just a DINO encoder. So if you've heard of DINO, then you'll kind of know how this works. But basically, DINO is this self-supervised model, basically trained in a way where, given some image, so you have some image, go with the cat again, like usual. So you have this image here, and you basically have this teacher model, and the teacher model is going to give you some encoding. So this is just going to be a really high level overview of DINO, because this isn't about DINO. They just use DINO. I think it's just DINO V1. V2 came out, and DINO V2 is crazy good. So you feed this through a teacher model, and this gives you some encoding. And then you basically take a patch of this. So let's say we take this patch here, and so we have this little patch here, and it'll just be kind of the corner of the cat's face, like that maybe. Now you feed this through a student model, and then this spits out an encoding. We'll call this maybe sub s and e sub t. You want these to be basically the same. So basically, the student, given less information, has to kind of come up with a representation of, like a good representation of this image to kind of match what the teacher has learned. But basically, it's a self-supervised method that, given an image, it gives you an encoding. That's the big point of it. But yeah, basically, it's just self-supervised learning, student teacher, and yeah, that's all I'll go into for that. But so it gives you this output here, which is 32 by 32 by 768. So you give it this image, 512 by 512, or 512 by 512 by 3. You just throw that through DINO, and this is DINO. It's just a VIT, a vision transformer, and they use transformers throughout this, like you do. You always use a transformer. So you give it this image, you encode it using a convolutional neural network, and you send it through DINO, and it gives you your encoding out. Now, DINO is going to give you some encoding, just class encoding, which is your embedding. So it'll give you a bunch of tokens, because you basically patchify your image before you send it through. So before you send it through DINO, you basically patchify the image because it's VIT. And you basically have these individual tokens, and the tokens are 32 by 32, or there's 32 by 32 tokens. That's the number of patches, and then there's they're each of dimension 768, and these all represent encoded patches. But it gives you a class token, and this class token is basically used for this self-supervised approach up here. But they take all the encodings because you need a lot more. Like, one encoding isn't enough to kind of represent this whole 2D image here, enough so that you can reconstruct it into a 3D image. So they take all the outputs of the DINO model instead of just the class token. And that gives these embeddings right here. So basically, we now have this 2D representation of our image, which is 32 by 32. That's our sequence length. By 768, which is our feature size. And this is our 2D encoding, and we want to decode this to a 3D object. Now, the second part is here. Basically, I'll just show this over here. So you start with your image, throw it through DINO, you get out your image encoding. Now, what they do is they take these positional encodings. So we want to decode this to some three-dimensional space. I'll just go to the three-dimensional space. So our three-dimensional space is going to be represented by a triplane. So it'll be 3 planes, and if you basically take 3 points, x, y, and z. So you can give me 3 points, and I can give you a point in this three-dimensional space based off those 3 points if we have perpendicular triplanes. So the idea is that we just want our model to model these triplanes here. So the output of our transformer, the end goal is basically, or the end goal of our transformer is to output this 64 by 64 by 3. And basically each of these triplanes will have 64 by 64 encodings to it. And you can think of the positional encodings as just like hopping along this plane here. So that one there. And the first positional encoding may be this spot, and then this spot, this spot, this spot, and so on. And then you can think you just concatenate that. So that would be our first plane. And then the second plane will have the same idea. So maybe we look at this plane, and the positional encodings would just represent some ordering along this plane. So that's the idea. We want our model to model these triplanes. We don't want it to model this volumetric space, because the volumetric space is expensive. We want it to model the triplanes because we just need 3, like a volumetric space would be 64 by 64 by 64. It's very, very large, but we can compress it if we use 3 by 64 by 64. And this actually isn't going to be 64 by 64 by 3, or it's actually going to have an embedding dimension as well. So our embedding dimension, I think it's 80. So each point on here isn't a point, it's actually a 80-dimensional vector. And we'll get into how that's used later. But just think of this part here. We want to model 3 triplanes. And these three triplanes allow us to pick any point, any combination, linear combination of points here. So we can get any point in this volumetric space here. And this volumetric space is how we're going to model our resulting object. So right now we have our two-dimensional encodings. The way we're going to generate this is we give it these positional encodings here. So the positional encodings are just going to be 3 by 32 by 32. So this represents our triplane. So you have 3 planes, and the resolution of each plane is 32 by 32, which is expanded later in a convolutional neural network. And we have an embedding for each point on those planes. So we have these positional encodings, and this is basically our sequence length. So 3 by 32 by 32. And a normal transformer, that's your sequence length here. And this is just your embedding dimension. Now, you just send this through a transformer. This is just your base, what you're going to do self-attention with. And if you've looked at attention is all you need, you know that you can condition a sequence. So if we have this sequence here, we can condition it on another sequence via cross-attention. And that's all they do here. They just do cross-attention using the 2D image on the positional encodings. And the idea is that as the transformer kind of changes the positional encodings, as it's conditioned on the 2D image, it'll slowly get an understanding of how this 3D representation needs to look. So yeah, you just send it through these you send the positional encodings through the transformer, conditioned on the 2D image, and you get out your triplane encodings. You then expand the triplane encodings, so it has a really large, this is 1024. So if we, in a way, it's kind of like a U-net, except you only have the top part of the U-net. With the U-net, you have a lot of channels with a small resolution. And at the top of the U-net, you have a large, very high resolution with few channels in it. So basically, you compress the number of features you have. So here, you basically compress the number of features and expand the resolution. And you do this through what's called it's a deconv or a inverted convolution. Basically, you're just you're decompressing the feature space. You're decompressing the features into the resolution to get a higher resolution embedding. And that's shown here. So you start out with your positional encodings. We'll get into what that is in a sec. And you have your cross-attention. So cross-attention just takes this encoding here, and it throws it through the attention module. Cross-attention is formulated, if I remember correctly. So we all know QKV, queries, keys, and values. I think the keys are going to be your two-dimensional data. Your values are going to be your two-dimensional data, and then your queries are going to be your positional encodings. But you can basically formulate this so that the shapes work out and the output is the exact same shape as the positional encodings. Kind of a hacky way of doing this. It's how they do it in Stable Diffusion. So you basically have your matrices, you multiply them in a way so that the output is the same shape. It retains the shape, but it conditions it on the 2D image, or in this, on the 2D image encodings. So if you ignore this, if you ignore these M's, you basically have a normal decoder network. So you have your cross-attention, you have your residual connection, you have your self-attention, you have residual, and then you have your MLP, and then another residual, and you just stack these. You just stack these layers over and over again. You get out your output, which is 3 by 32 by 32. That's your sequence length, that's your embedding dimension, which is the same as the input, as a transformer does. And then you do your deconvolution, where you basically uncompress your features. So you decrease the feature size, and you increase the resolution. So the resolution basically doubles for each plane. You go from 32 by 32 to 64 by 64, and your dimension, your embedding dimension, goes down from 1024 to 80. And yeah, you can reshape this, and you basically get your triplane, which is 3 by 64 by 64 by 80. So that's our triplane. I will get to this after the last part of the model. So last part of the model is, so we basically have this three-dimensional triplane, and on any part of the triplane, we can get these embeddings. Now the embeddings are kind of useless because it doesn't really, like, it's just some embedding. But what they do is they use a NeRF model. Now a NeRF model, basically a NeRF model given, say, x, y, z, you throw this through a NeRF model. So given x, y, z, you've probably seen a NeRF model before. It's basically the model itself. So this model here is like maybe a few linear layers, at least for the original NeRF model. And then it'll output some information. I think it was like the camera orientation, or maybe that was the input. But basically, it would output like the RGB, so RGB, and then the density. Yeah, and this you give it your camera angle, and I think you also give it the orientation, but you give it your camera info. So where is it kind of like looking at on the scene? And then you have this like 3D model here. Maybe it's like some face looking thing. It looks like that. So your model represents your entire scene, and in this case, it would be some 3D scene. And you basically query the model for XYZ positions, and the camera orientation, and it basically gives you kind of the image there. So this would be the output, and this would be the kind of hidden representation of the model. So yeah, that's kind of what you're going to get with the NeRF model. So the NeRF model is you get one pixel output for you basically query the model, and it gives you a pixel output. It'll make more sense in this context, I feel like, since it's slightly different. So basically, in this NeRF model, you give it x, y, z. So you query x, y, and z here. This is our x point, this is our y point, and this is our z point. And remember, each of these points is actually an embedding. So we don't actually have three numbers. We actually have three vectors. And these are our point features. And basically, we're saying, what does it look like? What does our output image look like at this point here? And in this case, maybe it's like nothing. So this will output, so this outputs the RGB and density. RGB and density. So at every point here, you get three values. You get the R, the G, the B value, and the density. So maybe for this point here, it gives you a density of 0, meaning that it's just nothing. So it would look like nothing. But maybe if we look at the origin here, we give it the origin, maybe that's this point here, and it gives you some yellow RGB combination with a high density. So our MLP gives us that. Our MLP is just our NeRF model given XYZ coordinates, so some coordinate on here. You give it the embeddings representing that coordinate, and it decodes those embeddings to the RGB value at that coordinate. And that's our NeRF model, neural radiance field. Yeah, RGB and density. Yeah, so that's what it gives us. And then you can kind of render the image. using that, using some camera pose at some point here. But that's the entire model. We'll go over this in a sec. But yeah, basically you give it a 2D image, you send it through DINO. DINO then outputs an embedding. You then send the positional encodings through this cross-attention decoder attention network, and you condition it on your DINO embeddings. This will output some feature representation, some representation of your 3D space, which you then expand. You increase the resolution of that, and your resolution. After you increase the resolution, you now have this triplane representation. You can then send your triplane representation through your NeRF model, which then gives you your output. If you query the NeRF model for every point on here, it'll give you your output 3D representation of the model, or of the image. This is a massive architecture. This is really big. There's a lot of moving parts, but the nice part is your loss function is right here, and that's all you have to model. Your loss function is just the reconstruction of this here. It's just the reconstruction loss. So I said I would get to this. That's just because it's kind of it's not as much machine learning as it is more. I think it more has to do with like rendering in video games and how you position the camera correctly. So it's not really machine learning. However, it is interesting because they mention that having this information helps a lot. So basically, let me go down here. They say they have these camera features, so they construct the camera features C in R20. So the idea is, so we need these camera features. We need to encode where is this image. So let's say we have, let me move this over. We have a space like this. This is our three-dimensional space. X, that would be Y, that would be Z. And this is just going to be our training data. So maybe we have some ugly looking vase that looks like this. Like that. That's a vase. Maybe our vase has some fantastic, beautiful flowers that look like this. Wow, that is a vase with flowers. So this is the 3D model that we kind of want to represent, and we want our model to learn from. So this is training data, and we now need to kind of get an image of this data. So let's say we kind of have a camera here, and our camera will give us some 2D projection of this three-dimensional space. And let's say it kind of looks it has this field. It has this receptive field. So the receptive field picks up, a camera. It picks up this three-dimensional shape, and it'll give you an output image. Now, the output image is actually going to be, it's not directly on the camera. So if this was like your camera here, your camera lens, then the output image is actually, there's a focal length to it. So focal length. Like that. And it's actually, it's not exactly where you would capture it, where you think you would capture it. And this gives you your output image after processing and stuff like that. So let me draw this like that. So this is some 2D shot. If we have a camera right here, it looks at the scene and it basically grabs the 2D image there. And yeah, so that's the kind of the setup. And you can move this camera around anywhere you want because you have this 3D model. Now, The idea is we want to give the model information on where the camera was, kind of what position was it in, to inform the model, instead of it just saying, oh, I have an image, I have no idea where this is at. Now I have to reconstruct the whole entire image from that. That would make it quite difficult for the model to learn where this learn where the image kind of fits into the 3D model. So they give it a bunch of information. The main kind of piece of information is called, it was called the extrinsic camera, the extrinsic matrix. So E is the extrinsic matrix. And this extrinsic matrix basically has kind of two main parts to it. So let me just write out kind of the default form. R22, R23, R31. TX, TY, TZ, and then there's 0, 0, 0, 1. So this is the matrix here. And this upper left part here basically represents, this is your camera rotation with respect to the axes. So basically with respect to these axes here, where is kind of the camera? So you can model that using these here. And what we're trying to model is so if this is our camera, and this is our world, we're basically trying to model a camera to world representation or a transformation. Basically, the model doesn't have to learn this transformation. It can instead use these features that are automatically created and that are used in like video games and stuff. These camera to world transformations to form a 3D object to kind of inform the model where the camera's at. So this upper part here, this upper left part, is the camera rotation with respect to the world axes. This part here is basically the camera position in the world. So this is the position, this is the rotation. And then this last part down here is just to maintain homogeneity, maintain that in the whenever you do a linear transformation using this 4x4 matrix. So this gives us 16 values. The other 4 values are mentioned over here. So there's 4 more values. There's x, foc x, foc y. So that's just the focal length. And this is ppx, ppy. So this is the focal length. And ppx, ppy is basically just the point kind of on the camera. What did they call it? They called it the principal point. And I'm definitely not explaining this as well as it needs to be explained, this part here, as this is not where my knowledge resides. I don't know much about the camera part, but if you are curious in this, it's camera features. This is the 4x4 extrinsic matrix. It's basically just informing the model where is the camera according to our 3D model. So you move this camera around, where is it at, so that the model knows where the camera's at with respect to the 3D model, instead of just taking a random 2D picture and giving that to the model. So just more information, and the model can use that. If we go back up here, you put it right before every module, and this actually acts as a normalization. They model the so it acts as a normalization right here. Basically, you do a layer norm. So this gives you your layer normalization, basically zero. It gives you a 0 mean and a 1 variance, or 0 mean, 1 variance, and then the model learns how to shift. So how to shift that around. So it has a learned mean, and then it has a learned variance. So you have a distribution, like so. Your distribution is all out of whack, maybe. I'm going to represent it as a normal distribution. Maybe it's very small, and it's all the way over here. You then zero mean one variant, so you kind of shift it and you standardize it. And then the model can learn where to move this. So maybe it wants to move it over here, and maybe it wants to expand it a little bit larger. You then shift it by 1 plus gamma, and gamma is just some linear combination of these features over here, of the camera features, and then you shift it by the camera features as well. So basically, you just normalize it, and then it learns a mean and variance according to the camera features. So it's just helping the model out a little bit. Yeah, so that's the entire model. Now the loss function is right here. The loss function is simple. So like a simple loss function is amazing. Having a simple loss function, you can't get much better than that. Usually whenever you have a model like this, you have a really complicated loss function, but literally all they do is the mean squared error between the ground truth and the prediction for the pixel for the pixels in the output, or I guess voxels. And they do it. They also have this other loss here called the LPIPS, and basically this loss function is supposed to kind of model human perception a little bit. You basically feed these both through some type of model. So you feed the prediction through a model, and you feed the ground truth through a model, and you basically do you compute some similarity. Maybe that's MSE between all the activations in the model. So if I have, I'll represent it as an image. That makes it easier. If I have some image here, so this is going to be our ground truth image, and then I have a reconstructed image. We'll call this X, and this will be X hat. You basically send this through the model. So the model is going to have a bunch of layers in it. Yeah, we'll draw it like that. So this is the same model here. I'm just drawing it twice. So this is our model. It has some features, and then maybe it gives you a class output. Or maybe it predicts 0, 1, something like that. Maybe this is some ImageNet classifier. So it would actually have like 100 classes here, more. But the encoded images, you basically do MSE for the activations between all of the layers for both these images. And the idea is that this basically it matches human perception. So instead of it being like pixel reconstruction, a direct reconstruction, it's more of a visual reconstruction, at least hopefully, assuming you have a good model. So this is just some model. Maybe this is some ImageNet, ResNet model, something like that. But that's your loss. It's reconstruction loss along with this extra loss. Basically make it more visually appealing, make the output more visually appealing, in case the reconstruction isn't perfect, because it's not going to be. And you do this for V total views around the image. So basically you just take a ton of views, you give that to the model, and the model tries to reconstruct this, and that's your loss, given those views. Now that is the entire model. They do some extra things. They normalize it. So basically the shape of the output box is -1 by 1. So that would be this box here. They just normalize everything because normalization it helps the model. You don't have exploding values. Yeah, the rendered images are of resolution 1024 by 1024, and the camera poses are sampled from a ball, radius 1.53, with the height of that. So if you're curious, they have all of the training details in here. Here are some examples. Yeah, so training. They train this on 128 NVIDIA A100 GPUs, which is absolutely insane. Of course they do. Of course they train it on 128 NVIDIA GPUs. That's quite a lot. Yeah, so that just means that you probably can't train this yourself. And it only takes 3 days. Only 3 days to train if you got 100 GPUs. And then inference. So inference, basically it takes an arbitrary image as input. So you give it some image. So squared and background removed. So you have to remove the background. They don't model the background at all. If we look at these views, it's just a white background. They don't want to try modeling the background. I think that would make it quite difficult to try to model the background because it's very ambiguous. And it assumes the unknown camera parameters to be the normalized camera that were applied to train the data. So basically, whatever the default camera position was, they assume that that is the position of the given image that you have. And then they query 384 by 384 by 384 points from the reconstructed triplane NeRF and extract the mesh grid using marching cubes. So they basically query this right here a bunch of times to get the output mesh using the NeRF model. And they say the entire process only takes 5 seconds to compute if you have an A100. So it's pretty fast to get this reconstruction prediction. I don't think there's anything else besides that. Yeah, features. The output scores aren't like there's nobody competing with this model, so the output scores aren't that interesting. At least in my opinion, yeah. More layers, the better. So yeah, and then they have some more images because like they're the only ones who have really done this well on this task, from what I know. So that they're not really competing with anybody. They don't really have a good baseline. Yeah, that's the model. It's pretty massive model. You got VIT, you got this cross attention, you got this output NeRF model. They're really throwing a ton of stuff at it, and it looks pretty good. It looks like it's getting there. The output meshes are pretty good, and I thought this was a pretty cool paper, different from the normal LLMs and diffusion papers I see all the time. So yeah, nice change of pace, and looking forward to seeing how well this model actually performs. Like usual, I don't think they open sourced it, so we will see once somebody creates or somebody recreates this paper. But it looks like it has promise.